And we are back. I may need a whistle. Maybe that would help. Yeah, I can't do that, and it bothers me. It makes me mad. And my fingers are gross because they touch everything. I don't like putting them in my mouth if I can avoid it. I know, I should. I'm a referee. I have lots of whistles. I should just bring one and see if that helps. Of course, you could argue, Isha, that I am plenty loud. It's not like you can't hear me. All right, so remember back in the day when you were in probably about grade 5 and Mrs. Bad Crumble asked you to make what she or he, if you had a Mr. Bad Crumble, described as a factor tree. Now, factors, Mr. or Mrs. Bad Crumble explained, are simply what? They're not variables. They can be. Two numbers that multiply together to make a product. Need there only be two, Sam? No, I can have as many factors as I need, yes? For example, 2 times 3 times 5 is 30. So 2, 3, and 5 are all factors of 30, yes? Excellent, okay. So Mrs. Bad Crumble or Mr. Bad Crumble taught you that, and then you drew a bunch of these factor trees. Some of your Mrs. Bad Crumbles drew them downwards. Some of your Mrs. Bad Crumbles drew them sideways. But they were all following the same basic concept. And then Mrs. Bad Crumble gave you some homework. You went home, you drew 100 factor trees, even though you understood the concept after 10. She made you draw 100, that's fine. Then you came back to school. Mrs. Bad Crumble gave you a test on which you did 2 or 3 more factor trees. You did it or didn't do it. And then whether you did it really well or didn't do it at all, you were moved on to the next grade of math. Yes? Excellent. Never once learning why you made a factor tree. Did you? Till today. Unlike every other country in the world, we Canadians like to teach you a very little tiny thing in math and then never talk about it again for 5 years and then expect you to be good at it now when the last time you saw it was 5 years ago. Of course, right? You should all take all your driving tests when you're 16, but not actually drive a car till you're 21. That makes good sense, doesn't it? So, we're going to use these factor trees now for what they are actually good for. But before we do that, I have to remind you of yet another concept from your Mrs. Bad Crumble days. Prime numbers. Those happen to be 3 of the infinite amount of prime numbers, but yes. Well, I was going to ask, Riley, if anybody remembers what a prime number is. Jack?
It's a number that multiplies itself by either itself and 1. It only multiplies itself with itself and 1.
Okay. That was a very roundabout definition, but he did cover... Oh, this is really frozen solid. I can't even fix this. This might be a shutdown situation.
Everybody get down.
Yeah, it is. Oh, yeah, no, I know, but the display is not working. I'm going to try plugging in the keyboard. Oh, I saw something there. Oh!
Maybe if
It could be the pen. That does happen. The pen often unpairs because, quality. Wonderful. Lots of people's phones are showing up.
My phone hasn't shown up yet. I don't know. I'm probably on this phone. No. Let's see, is my Bluetooth on? My Bluetooth is on. Oh, my Bluetooth is on. My phone's not phone too. That's a Fitbit.
Oh, somebody's making sure they're fit. Ooh, a Galaxy A5. Dumb phone 2, that's a good one.
Hey, that's mine.
What happened to dumb phone 1?
That was my iPhone 4. It's gone. I made it to an Apple Watch. I gave it to my own.
So as I was saying,
Chef Boy RD.
that's funny too. As I was saying, a prime number nope. As Jack said, a prime number has two factors. One and itself. What does that mean? That means that only the number 1 and the number with which you are working will divide into any given prime number. I expect, well, I don't expect, but it's a very good idea for you to memorize the first about 10 of them. They are 2, 3, 5, 7. What's next? 11, then 13, then what? 17, 19, 23, 29, 31. That's useful. Okay? What is special about that one?
It's an even number?
It is the only even prime number. There we go. So, you already know what a prime number is because I don't need to write it down. But what we are going to do now then is we are going to make one of those factor trees like you learned with Mrs. Bad Crumble. And you're going to stop the factor tree, any branch, when you get to a prime number. So the first thing we have to decide are any two factors of 54. What are they? 9 and 6. Are either of those prime numbers? No. So can I stop my branches there? No. What does 9 break down into? 3 and 3. Are those prime numbers? So I stop there. What does 6 break down into? 3 and 2. Are those prime numbers? So I stop right there. So, if I was going to write the prime factors of 54, I would write 2 times 3 times 3 times 3. Yes? Now, us being grade 10 math guys now, not grade 5 math guys, what would I write instead of 3 times 3 times 3? 2 times 3 to the power of 3. Nice job, Tasha. Now, 162. Do it there.
54 and 3.
54 and 3. Prime number, stop. And then 54 we're already done. 9 and 6. 3 and 3. 2 and 3. Now, how would I write out that one? 2 times 3 to the 4th power. Yeah? Yeah? Yeah. Why? Well, you spend a lot of time talking with Riley about things that aren't math, and then you try to catch up now, even though I've been explaining it all the way along. It is a little bit your bad. Thank you for recognizing it.
What I don't understand is say it multiply like by 1 and itself. So
Yep.
multiply it by itself, so it's like 54 times 54.
No. A prime number has two factors, like 1 and 19. There's no other numbers that will multiply together to make 19 except 1 and 19.
Okay, so it's just 1 time.
Oh, I got enough.
Now,
I just realized.
what's weird about prime numbers is they don't end. Math nerds just found the biggest prime number ever, and it's up in the billions. So this number that has 10 digits in it has no other numbers that will multiply to it except 1 and that 10-digit number, which is pretty mind-blowing when you think about it, right? Because look at how many factors a little number like 54 has, right? It's got 4 factors, whereas a number like 20 billion something has none but itself and 1, which to me is, you know, even if you don't think about this stuff, you only think about it for this 1 second that we're talking about, it's pretty wild. What?
It's also stating how much time that they have on their hands.
Well, no, a computer does it. They don't sit there with a pen and paper. A computer's doing it. Anyway, so I'm going to stop for a moment because making these factor trees is really, really easy if you're good at multiplication. If you've actually memorized your times tables. Almost none of you have. You were taught a bunch of crazy tricks like 9 times 7, 63, right? And all that stuff. For some strange reason, it's okay to give you guys tricks to memorize, but it's not okay to get you to memorize the actual timetables. That makes you a bad teacher if you say memorize your times tables. But it's okay if we say memorize all these stupid little tricks.
What should we know?
You should know your times tables reliably. You should know them reliably up to 20. You should have them memorized up to 12. And when I say memorized, I mean this. 7 times 12. Too long. You don't have it memorized. No, 84. Right? Doesn't matter. If it's memorized, Sam, if it's memorized, you don't need it expected. It's right there. That's what memorized means, right? Right? Like you know when you pour a bowl of cereal, your next step is to go get milk, yeah?
Sometimes.
Wait. You're telling me that
So-
you pour your milk before your cereal?
Now,
I'm saying that
because a great many of you do not have your times tables memorized, and you learned all these crazy little tricks, it stands to reason to me that you were also taught tricks for division. But I have been informed that you were not taught tricks for division. So you were not taught to memorize the times tables, nor were you taught ways to do division. So in case, while you're making your factor trees, you're in a bit of trouble, I like to make sure that you have some division tricks available to you. So if you know division tricks, don't worry about it. If you're good at your times tables, don't write down what I'm about to write down. But some of you may want this. So I'm going to quickly write a couple of division tricks over here. The first one is this. If your number ends in 0, 2, 4, 6, or 8, you can divide by 2 because it's even. The second trick I would like to give you, if the digits in your number add to anything, you can divide by 3, then your number divides by 3. Let me give you an example. 123. What's 1 plus 2 plus 3? 1 plus 2 plus 3 equals 6. Does 6 divide by 3? So that means 123 divides by 3. Okay? The third one that I like to give you, if it ends in 0 or 5, you can divide by 5. And the last one I like to give you, if you can divide by 2 and you can divide by 3, you can divide by 6. Jack.
One I learned is that if the factors add up to 9, you can divide by 9. It's like
By
9.
9. Yeah. I don't usually go past 6 because in grade 10 we're looking for prime numbers, right? And 2, 3, and 5 are low prime numbers that we're going to use a lot of. But yeah, that's another good one. Jack just gave us another one. 5. If the digits add to 9, then you can divide by 9. Cool. There are some little tricks to help you along the way making your factor trees. Because, of course, when you were in grade 5, your factor trees were of little numbers, weren't they? But, as we learned yesterday, numbers go up to what? Infinity. I just told you there's prime numbers in the billions. So it's good to have a couple of these tricks up your sleeve if you don't actually know your times tables. Cool? All right. Now, let's go on with this. A greatest common factor, which is abbreviated to GCF. A greatest common factor is the largest factor. And remember, a factor is just anything that multiplies together that is shared by a group of numbers. And you can find the GCF using prime factors by doing the following. If you multiply all of the factors shared, please underline shared, between your group. So I'm going to use black ink, and down at the bottom of the page here, I'm going to do the GCF of 54 and 162. So the first thing we do is we take the factors of 54, which are 2 times 3 cubed, right? Right? And then we take 162, and we know that it is 2 times 3 to the 4th, right? Now, to find the GCF, I have to multiply all of the shared factors. Is there a 2 in both of them?
Yeah.
So I'm going to multiply something with a 2. Is there a 3 in both of them? There are 3 3s in both of them. So I'm going to multiply by 3 cubed to get an answer of 54. Does that make sense? Is 54 a factor of 54? Yes, because 1 times 54 is 54. Does 54 go into 162? Yes, because 50 times 3 is 150. 4 times 3 is 12. 150 and 12 is 162. Everybody good? Sweet. Now, let us go on to talk about the lowest common multiple. which is the LCM. You guys already know how to do this. You use lowest common multiple all the time, but you don't call it lowest common multiple. You call it lowest common denominator. Because when you're adding fractions, you need to change those denominators to be the same. And how do you change those denominators? By multiplying them. Multiple, multiply. The lowest common multiple, and I'm going to write that all in blue because I'm going to do all my lowest common multiples in blue. The lowest common multiple is the smallest product of your group. And the lowest common multiple can be found using prime factorization again, and this one's a little tricky, by multiplying all of the factors. Now, what word am I not writing now? I wrote shared. Am I writing shared here? No. All of the factors once only. Now this one's tricky. I need you to pay attention to it. We do it the same way. We start the same way. 54 was 2 times 3 to the third, yes? 162 was 2 times 3 to the fourth, yes? I need to multiply everything once only. So, if I multiply by 2, does that cover all of these 2's?
Yes.
Yes. If I multiply by 3, does that cover all of these 3's?
No.
No, it only covers one of them. If I multiply by 3 squared, does it cover all of them?
No.
If I multiply by 3 cubed, does it cover all of them? If I multiply by 3 to the fourth, does it cover all of them at least once? Yes. So that is 162. And we know that is true because we know 54 times 3 is 162. And we know 162 times 1 is 162. So 162 is the lowest common multiple. Is everybody good? You need practice on it. So turn the page over and make your factor trees for, I can't remember what the first numbers are. 36 and 120 it is. Make your factor trees. However you want to make them.
Riley's flexing on us.
Everybody should have been able to get to there quite easily.
Yes.
Everyone is good? All right. Let's work this out now. What, Nick? Oh, okay. If you have done this, attempt to find the GCF. Remember, GCF is only what is shared. How many 2's are shared? 2 squared. How many 3's are shared? 1. Are any 5's shared? No. So what's the GCF? What is 2 squared? 4 times 3. And what's 4 times 3?
12.
12. Everybody good? All right. Now let's do the LCM. How many 2's must I use to cover all my 2's? 2 cubed. How many 3's must I use to cover all my 3's? 3 squared. I heard someone say 2. Now, do I count the 5 in LCM? If you don't remember, look back at your notes. Do I count everything once? So do I count the 5? Yes. What is 2 cubed? 8. What is 3 squared? 9. What is 8 times 9? 72. What is 72 times 5? Not really. What's 70 times 5? Don't go to your calculator. Stop. What is 70 times 5? 350. What's 2 times 5? 10. What's 350 plus 10? 360. Everybody good? Everyone is good? All right. Let's do 18 and 24. What is 18? 9 and 2. Can I stop there? No, because 9's not a prime. So 18 is 2 times 3 squared. What about 24? 6 and 4. Can I stop there? 2 and 2. 2 and 3. Can I stop there? So 24 is 2 cubed times 3. Yes? Agreed? Okay. What's the GCF? How many 2's are common to both of them? A 2. How many 3's are common to both of them? 1. What's 2 times 3? 6. Lovely. Now let's do the LCM. How many 2's cover all of them? 2 cubed. How many 3's cover all of them? 3 squared. What's 2 cubed? 8. What's 3 squared? 9. What's 8 times 9? Nope. 72. It's not memorized. But you know that trick. 8 times 9, you make the 9, the 8, you got to go 7, and then 7 plus 2 makes 9, so 8 times 9 is 72, which takes way longer to learn than 8 times 9 is 72. But it's okay to learn those tricks, not okay to memorize times tables. Now, I want to show you a little trick. What do you notice about everything that I am highlighting in green? What do you notice? When you're doing LCM, what did you do? The highest exponent for every number is what you need to use. What exponent should 5 have? 1. What exponent did I use? 1. Everybody cool? Okay. You try the next one. 45 and 75. Real easy. Why? Because they got 5s. What's my GCF? Why? because 1 3 is shared and 1 5 is shared. What's my LCM? 3 squared times 5 squared. What's 3 squared? 9. What's 5 squared? What's 9 times 25? 225. LCM, GCF. Good? Let's do the last one. 35 is what? 7 and 5. 84 is what? 21 and 4. Now what? 2 and 2. And 7 and 3. So I've got 35, 7 and 5, 84, 2 squared times 3 times 7. Yes? What's my GCF? Seven. It's the only thing that's common. What's my LCM? How many 2's do I need? 2 squared. How many 3's do I need? 1. How many 5's? 1. How many 7's? 1. The biggest exponent of any number. Not quite. 420. That's when somebody starts giggling. Now, ladies and gentlemen, this is where I'm going to do something that shouldn't cause any problem, but will. I am going to expand this group to add a third number, 30. And I'm going to expand this group to add a third number, 16. What do? I do the same exact thing. But some people are going to say they can't do it when there's 3 numbers. What are the factors of 30? 3 and 10. Stop at 3. What about 10? 2 and 5. Stop there. So I come down here and I add 30 to my party. 2 times 3 times 5. What's my new GCF? No.
It's still 5. Oh wait, it's still 15.
How many 3's are common?
3.
No.
4.
1. This guy has 2 3's, but these guys only have 1. How many 5's are common? 1. This guy has 2 to give, but these guys can only cover 1 of them. So my GCF is what? Still 15. What's my new LCM? How many 2's do I need? 1. How many 3's? Squared. How many 5's? 5 squared. 2 times what's 3 squared? 9 times what's 5 squared? 25. What is 25 times 2? What's 50 times 9? 450. What happens when I add 16 to this party? What is 16? 2 and 8, 2 and 4, 2 and 2. So 16 is 2 to the 4th, yes? So what's my GCF? What's common to all of it? Nothing. So what's its GCF? What? 1. Because 1 goes into everything. What's its LCM? What do I need? Count everything once. How many 2's? 4 of them. 3's? 1 of them. 5's? 1 of them. 7's? 1 of them. 2 to the 4th is 16. 16 times 5 is 80, times 3 is 240, times 7 is 240 times 7. 1,400, 1,680. Can everybody do this? And it never gets more difficult. You just have to be able to break down the numbers, look at what's common. You are going to do page 90 for me. Now listen to me, please. Something weird has happened. Before you go off on your own, you're going to do that now. Hold up for a sec.